David Clayton and Nick Jones developed the Mark I ATMP primarily for agricultural use. However, after the Falklands War, the UK MOD found a capability gap for a low ground pressure all-terrain vehicle to carry large payloads. They took around 200 ATMPs, with a further 50 going to the Malaysians and one further vehicle for the MAS team conducting autonomous research. The ATMP was used effectively in the recovery of containers of combat supplies on the drop zones and moving them to the safety of the tree lines before supporting the brigade during their advances to battle. The utility of being air transportable, amphibious, able to carry huge payloads and have an extremely low ground pressure made it a soldier's favourite, and it's now hugely missed. The opportunity that the eATMP gives is the same outstanding performances with a leap forward in technology. And here we are at the present day. This is the eATMP. Back in 2017, Supercat formed a knowledge transfer partnership with the University of Exeter with the aim of electrifying the ATMP. I was fortunate enough to be the prime candidate for the KTP, joining the Supercat team. The KTP aims to transfer knowledge and allow universities to get their research into companies and into, therefore, products that are out in the market. Our KTP programme was geared towards using the ATMP as a testbed for further new technologies, with the first programme of design and development was to convert the vehicle from diesel power to electric, which successfully concluded in 2019, where we received a prestigious outstanding grading from the expert panel. We've replaced its traditional diesel engine with 6 electric motors, with one attached to each wheel, and this can be configured for full electric or hybrid variants. The eATMP retains a lot of the excellent features that the standard ATMP had, including the 45-degree approach and departure angle, the large, low ground pressure tyres, allowing it to have the ground pressure less than that of a human footprint. It also enables one-handed operation using the hand throttle. There's also a foot throttle as well. Users of the original vehicle may remember that the vehicle had skid steering. This was operated hydraulically. Nowadays, we can use the electric motors to lock on the inside using this thumb control. The vehicle also retains the Ackerman steering, allowing the front to steer more than the centre. This keeps it stable on road and allows it to travel up to speeds of 40 miles an hour. It also retains the large load bed that allows it to carry a standard NATO pallet. As well as this, it can be underslung from various helicopters, as well as being stacked one on top of another and loaded into the back of several different aircraft. Here's a video of me at the test track taking this out for a spin. The ATMP is the world's most popular, versatile off-road vehicle of its type. So the new technology in the eATMP opens up the market for emergency services, rail, marine, forestry and aerospace, as the electric drivetrain can be customised depending on the range, payload and operating environment. Crucially, when applied to other off-highway transportation, the electric drivetrain can be tailored and customised depending on the mission, range, payload and operating environment that each vehicle will be used for. It's a suitable vehicle for field hospitals or communication systems, and because the electric vehicles emit little heat or noise, the vehicle can be stealthy on the battlefield. Now the innovative, eco-friendly vehicle is being developed further so it can be optionally manned. I'll now hand over to Yash, who is the lead engineer of the Autonomous and Optionally Manned project.
Thank you so much, Matt, for explaining my role. I was designated as the main KTP lead for autonomy section, where we use the knowledge taught in academia and correlate with that in the industry. There have been research going on across autonomous sections. So here I'm going to be explaining you with the motion control of the vehicle. The first thing is how we control the drive. It's a 6 configuration a motor controllers over there which is connected to the master controller. The master controller is deployed with robotics algorithms that use dynamic and kinematic models. From over here, we use the control area network to define different commands to the systems. We use the master controller to switch between man and man functions with a flick of a switch. Starting on that, we move towards the sensors. A sensor suite is using vision sensors of cameras, which are displayed up on the top, over here, and at the back. We have got a LiDAR that uses the point cloud technology to make a 3D map of the surroundings. This forms the environment mapping section. Looking into the classification, we use neural networks. So for neural networks, we thought of using a GPU because we are getting a lot of microprocessor power. We need to designate these tasks to GPU. Over here is a master controller for the autonomous operations. It's an NVIDIA unit that uses Linux kernel based inside it. We use different algorithms which slowly amplifies the whole system around. Using these specific algorithms, we have converted convolutional neural networks to understand what classification we can give for the train. So when the main motion control commands are going in, we have another CAN network data that flows through the network. Coming back over here, the LiDAR and all these sensors are located with the inertial measurement unit. So changing the position of the sensor would change the quantitarian. That forms exactly the sensor fusion we require for the systems. Back over here, we have a location module. We have specifically put the location modules at the center of the vehicle to designate the main function of IMU. We also have the IMUs on the front and at the back at the master controller designated. This forms a complete simultaneous localization and mapping. Using these algorithms, we have put up different matrices that perform on the GPU. Coming back to the section of using the resources available on the vehicle completely, we have gone down to the level of using proper GPU kernels and using CUDA kernels to define how we are working through the mathematical algorithms. In this total, we have different functions. So looking on these systems, the vehicle can perform waypoint navigation, it can go for collision avoidance systems, it can shift between unmanned control, and all these operations are programmable on a PixHawk. The PixHawk unit is inside over here, which provides amplified units for localization sensors. Looking at the motion control aspect of the vehicle, we have got a 6 motor control configuration that is commanded by a master controller at the back. In this motion control equations, we have put up robotic algorithms which support the dynamic. It also uses the vehicle's coefficient of friction. We have different dimensions on the vehicle that can be included in the configuration. This defines the main motion control body, which is connected via control area network. Now defining on this main control section, we have an AI computer over here. Going back to the sensors, we have a suite of vision sensors, which is in the front, a 3D sensor over here, at the top and at the back of the vehicle. That is integrated with the LiDAR with the point cloud algorithm. To process this, we need additional power for a GPU. So the NVIDIA units provide us with that. We have additional units also for dividing the resource and using them quite efficiently. Looking into the back of the environment mapping section, we use convolutional neural networks to classify objects around. Classifying objects define how the vehicle drives in the motion area and what kind of obstacles are there. These decisions are checked with a confidence map. So look, coming back over here on the master controller and the front camera, this camera is a 3D point cloud camera. All these sensors are fused together using the sensor fusion algorithm that confines using Kalman filters. All this brought up together, it forms a simultaneous localization and mapping of the vehicle. This will be live happening on the vehicle, and we'll have data that we can be receiving on the back. All these functionalities will help in unmanned platforms. For example, we are using motion control, we are using mapping algorithms, we are using other motion control work that finally defines the path for using waypoint navigation, collision avoidance, classification. So all of this works together.
You may ask why we are investing heavily into electrification. Well, we see that the UK seeks to gain a performance advantages, and we have the engineering capabilities to be at the forefront of the electric revolution in the defence and off-road market. Let's see the eATMP in action. At SC Innovation, we pride ourselves on our continuous development and investment in electrified vehicles. Thank you for watching.